Now we are going to talk about a new method, a new way to compute the volume if you rotate a plane region around some axis, x-axis or y-axis. Okay. Now let's look at the question first. Okay. Can I make it a little bit smaller so I have more room to write things? Now look at the question first. I will show you a sketch. I will show you the sketch of the plane region. Okay. In any case, we need to draw a sketch. Okay. Can I squeeze the sketch at this location so that I have more room to write? It's really hard for me to draw straight lines. One curve is the curve with the equation y equals x squared, the same as before. The other curve is the curve y equals x. I think the plane region, this part is kind of the same as what we did the last time. Okay, you have a parabola y equals x squared. Okay, and you have a straight line y equals x, something like this. I think this point has the coordinate of 1, 1. Okay. To convince you, in some cases the new way is better. And by the way, the new way is called cylindrical shell, the method of cylindrical shells. You are going to see why we're calling it shells. Cylindrical, it means there will be cylinders involved. Okay. You are going to, all the terms will make sense very shortly. Okay, later. Now look at the plane region. Okay. This time you have a vertical line. This vertical line has the equation x equals 1/3. You project this point to x-axis. I think this point you have 1. Okay, and you also have a vertical line here. A vertical line has the equation y equals 1/3, x equals 1/3. Okay, so this is a point x value of 1/3. The vertical line x value of 1/3, x equals 1/3, divides the plane region R into two parts. We use R1 to denote the larger part. Okay. You imagine the whole vertical line. Now follow the mouse cursor. Okay. The whole vertical line is something like this, right? The whole vertical line divides the plane region into two parts. We use R1 to denote the larger part. Okay. Now let's try to locate the region R1 corresponding to 1/3. You have a little vertical line here. I'm going to shade something. Okay, the larger part, we mean that part. The vertical line x equals 1/3 is a vertical line something like this. It cuts the plane region into two parts. Now R1 is the larger part. Okay, I'm going to remove the shading, the same as before. Now we only concentrate on the plane region R1. Okay, we concentrate only on the plane region R1. Still, we need the equations of the curves. The bottom curve has the equation y equals x squared. The top boundary of R1 has the equation of y equals x. I will just say top boundary. We still need these lines. That's basically the setup. No, that's not the setup yet. Okay. Now look at the question. Now look at the question. In the question, we are going to rotate R1 around y-axis. Now imagine the plane region. Okay, we rotate the plane region R1, the shaded region I shaded earlier. we rotate the shaded region R1 I shaded earlier around the y-axis at this time. So don't be dizzy. We are rotating all the time around y-axis. Okay. Imagine the solid. Now you imagine the solid. In any case, we are talking about the new method first. Okay. I want you to imagine the solid, and then you follow the method. You follow me for the method. Okay. So temporarily, I will still shade something. Now I shaded R1. You imagine you rotate the entire R1 around the vertical axis, around the vertical axis. Okay. You have a solid. I think you have seen many questions. Now you can imagine the solid. Okay. Okay. Now follow me carefully. I will tell you how to think the whole thing, little step by little step. Okay. The first thing we do is to imagine the whole R1 is formed by many vertical line segments, by many small vertical line segments. Okay. That's one of the little line segments. That's one of the line segment. You just imagine this little line segment. You move this little line segment from left to right so that you can form the entire plane region. So does that make sense? Starting from the line segment in here, the line segment has the two endpoints on two curves, and then you move the line segment from this point, from x value of 1/3 to x value of 1. The little line segment, I mean, will trace out the entire plane region. I said trace out. Or alternatively, you just imagine the plane region R1 is formed by many little line segments. So does that make sense? Okay. The first step is still to get the interval on which we evaluate the integral. Okay. At this point, so do not ask me why. You just remember. So later on, everything will make sense. Okay. In step 1, the first thing we do is to project the plane region. R1 onto x-axis. X-axis. Good enough. Again, R1 is the larger part. Okay. Now look at the question. We use R1 to denote the larger part. A vertical line divides the whole thing into two parts. R1 is the larger part. Now we project the plane region R1 onto x-axis. Anybody want to tell me the interval? We get the interval. The interval, please. The interval, please. It's easy. We project R1 onto the horizontal axis. Yeah, the plane region is from 1/3 to 1. Okay. Again, you just think what is the smallest possible value of x, what is the largest possible value of x for all the points in R1. Okay. So we have the interval from 1/3 to 1. So later on, we are going to have a integral. I mean, we are going to have an integral over the interval from 1/3 to 1. So that's the integral we are going to evaluate the volume. Okay. The first step is that. Okay. The second step. Now follow me. Again, we imagine you consider this R1 is traced out by many little line segments. A typical line segment is something like that. I made it bold. Can I just say bold? The second thing you do is after getting the interval, the second thing you do is you choose an arbitrary value of x on the interval, the same as before for each x, for every x on the interval from 1/3 to 1. So basically, the corresponding x is here. The following argument is going to be true for any x. Okay. The value of x in between 1/3 and 1 will determine a little line segment, the very thick little line segment on the graph. I was trying to use that little line segment to represent the little line segment determined by x. Okay. This time you rotate the little line segment around the vertical axis. So because originally we wanted to compute the volume of the solid obtained by rotating R1 around the vertical axis, y-axis, right? Okay, so this time, in order to get the whole solid, we rotate this little line segment. So later on, I'm going to make more comments. But so temporarily, you just imagine you rotate this little line segment, the very thick line segment, around the vertical axis. Can you give me a description of the shape? Only rotate the little line segment around the vertical axis. So what do you get? Only rotate the little line segment around vertical axis. You rotate the little line segment around the vertical axis all the way. I'm looking for a description of. It's kind of a ring, but you just imagine this little line segment. It could be longer. It could be longer. If the little line segment is longer, it's still a cylinder. A cylinder is right. That's where it comes. Cylindrical shell. So we're going to see the cylindrical shell. That's the cylinder. The cylinder, we're going to call the cylinder cylindrical shell. So that makes sense? You rotate that little line segment around vertical axis, we have a cylinder. That cylinder is the cylindrical shell. Okay, it's a shell. For each value of x on the interval. Okay. So can I just say the cylinder or the cylindrical shell? By the cylindrical shell, I mean the cylinder. So Ben told me. Okay. The cylindrical. So basically, each x will determine a cylinder. Okay, will determine a cylinder. We're going to call the cylinder cylindrical shell. The cylindrical shell. It's kind of hard for me to describe the shell. So can I just say the cylindrical shell? So determined by x. By that x, the shell determined by that x. So later on we are going to okay. So later on we are going to use the area, the surface area of the shell to get the volume. So later on I'm going to make more comments, but temporarily now let's concentrate on how to get the surface area of the cylindrical shell. If you want, you can check the formula. You can search the internet for formula. without including the top and the bottom, only the surrounding bit, only the surrounding part. We need the surface area, so later on in order to get the volume. The cylindrical shell determined by x has the, in order to get the surface area of the cylinder, we need the base area, we need the height. Okay. Probably it's easier to identify the height. Okay, now let's get the coordinates of the point. Okay, so this point has x coordinate of x and y coordinate of x squared. I think we have seen that many times. If you know the x coordinate, and then the point is on the curve y equals x squared. So this point, I mean this point has x coordinate of x and y coordinate of x squared. And likewise, this point, the other end point of the little line segment has x coordinate of x and the y coordinate of x as well. So because it's on the line y equals x. Okay, now let's get the height first. So later on, we are going to get the base radius and the height. For the base radius, I'm going to use the notation r of x to denote the base radius. Now let's get height first. For the height, I'm going to use h of x. So because for different value of x, the height is different. Yeah, that's why I'm using h of x to denote the height. Okay, anybody want to tell me the height? The height of the cylinder? You have a little line segment. The length of the little line segment is going to be the height of the cylinder. So that makes sense? The length of the little line segment is going to be the height of the cylinder. So that makes sense? So can I just draw a little cylinder in here? Yeah, probably it's not going to be too messy. I hope it's not going to be too messy. The cylinder is going to be something like that. Now I'm looking for the height of the cylinder. So please get me the height first. What is the height, please? I'm looking for the length of the line segment. I give you the coordinates of the 2 points already. So please, you know that. Anybody? So let us try something, please. How long is that? Now look at the mouse cursor. How long is the line segment? The height of the line segment will give you the height of the cylinder. Right? That's right. X minus x squared is right. Okay, that point has y coordinate of x. That point has y coordinate of x squared. The difference between 2 y coordinates will give you the height. Okay. Okay, now the base radius, please. Base radius is also simple. So what is the radius of the base? The base radius, please. I'm looking for the base radius for this. I think you cannot see the cylinder. So what is the base radius of the cylinder? Base radius, if you want me to draw something, it's just that, right? X minus x is 0. Again, please, try again. Base radius is x. So that makes sense? Now look at this point. This point has x coordinate of x. Base radius is just x because the line of rotation, you rotate around y-axis. So does it make sense? The base radius is x. So please, I think many of you guys know that. I just need more people to answer my questions. So please. So that makes sense. You have now. Okay, now look at the cylinder again. Yeah, probably I'm going to try to. The base radius is nothing but x. Okay. Base radius is x. So does that make sense? Now you check your formula or whatever formula you learned in high school. Now for a cylinder, we know the base radius, we know the height. Now we are going to be able to compute the surface area of the cylinder. Okay. So the surface area, I was trying to write surface area. I will write the full name. The surface area of the cylindrical shell. I do not even want to introduce a new notation, but now let's get the surface area first. Anybody want to record the surface area of a cylinder? Only the surrounding part? For a cylinder, you just imagine you cut off the cylinder. Okay, I'm going to tell you the formula, okay? I'm going to use a new page to tell you what you're given a cylinder, okay? A cylinder. Now let's say the height is h, the base radius is r. So what is the surface area of the cylinder? Do not include the top and the bottom. We just need the surrounding part, okay? You just imagine you cut off the cylinder. You have a rectangle, okay? You cut it out, you have a rectangle, something like this. The height is the same. So what is the length or the base of the rectangle? Circumference of the circle, right? Is 2 pi r. Okay. So the surface area of the cylinder is 2 pi r h. You learned that in high school, or at least you can imagine. As long as you know the circumference of the base, the circumference of the circle, then you should be able to understand that. Okay. So the surface area of the cylindrical shell is, I do not want to introduce a notation even, okay. So that makes sense. It's 2 pi r of x, and then times h of x. In this particular case, you have so do not forget 2 pi, okay? 2 pi r of x. I think in this particular case it's x. I'm just plugging in the functions in. You have 2 pi r of x is x. h of x is x minus x squared. So we got the surface area of the cylinder determined by each x. The argument is true for any x in between 1/3 and 1. Okay. Okay. Now let's listen to me carefully. I'm going to make more points now. Okay. I will start from the beginning. The plane region R1 is formed by many little line segments. Now listen to me carefully. The plane region R1 is formed by many little line segments. Okay. Each little line segment will determine a cylinder, a cylindrical shell. So many little line segments will determine many cylindrical shells. many cylindrical shells will form the solid. So does that make sense? I will repeat later. Okay. Many cylindrical shells, many cylinders will form the solid. The solid after rotating the plane region R1 around the vertical axis. I hope it makes sense. You integrate the areas of all the cylindrical shells. You have the volume of the solid. I'm going to repeat. Listen to my point. The following point is trying to show you why the formula is true. Okay. I will start over. Now listen to me carefully. Okay. You have a plane region R1. You treat R1 to be formed by many little line segments, by many vertical little line segments. That's one point. Every little line segment will determine a cylinder. You rotate the little line segment, you have a cylinder. You rotate many little line segments that form the plane region R1. So many cylinders will form the solid. The volume of the solid is obtained by integrating the surface areas of many cylinders. I hope it makes sense. The same as before, we mentioned before, you integrate areas, you have the volume. Actually, the same idea. Okay. We're almost done. After getting the surface area of the cylindrical shell, we're ready to get the volume. Okay. Now we're on step 3. We're on step 3. Okay. On step 3 is actually the volume V. The volume is the volume of the solid. The solid is obtained by rotating R1 around y-axis. Okay, so the volume V. So this time is computed by integrating from 0 to 1. From 1/3 to 1. The interval you got in step 1. Okay, you got from 1/3 to 1. You integrate the surface areas of the shells. You have the volume. You just copy the function as the integrand. I think you have 2 pi x. Here you have x minus x squared dx. So that makes sense. Okay. A second method. Yeah, that's the second method. Okay. The whole method is called the method of cylindrical shells. Now let's say so -1 is here. You have a vertical line, something like this. Yeah, something like that. Okay. This time we are going to rotate the entire plane region R1 around a different vertical line. So this time I did not draw anything in between 0 and 1/3. I hope the meaning will be clear. Okay. Still, we need the equations of the line, and the equation of the problem, the curve. Now let's recall the curve has the equation. The curve has the equation y equals x squared. The top line has the equation y equals x. Okay. The setup is kind of the same. You draw a sketch first, and then we get the interval. So keep in mind, so this time we do not project the solid, we project the plane region onto the horizontal axis. That's x-axis, right? The plane region to emphasize, I still read the full sentence. We project the plane region R1 onto x-axis. We get interval, please. I think the same. Yeah, probably you don't bother to answer me. Yeah, from 1/3 to 1, the interval from 1/3 to 1. Okay, so because we have the same plane region, right? The second step is kind of the same, so just the height or the base radius are going to be different. We are going to see. Okay, for each value of x in between 1/3 and 1. Of course, you still need to imagine the shape of the solid. You need to imagine for what thing we're going to compute the. You got it, Chad? I think Chad got it. The base radius is right. Actually, the height is the same. Is that right? I think Chad got the whole thing. For each x in here, now we choose an arbitrary x in between 1/3 and 1. Okay. Again, you use a vertical line to cut the plane region. You have a little line segment. You have a little vertical line segment. Choose an arbitrary x in between 1/3 and 1. You have a little vertical line segment. Okay. Still, we need the coordinates of the points to get the height, I believe. This point has x coordinate of x and y coordinate, I believe, x squared. We have seen this many times. This point has x coordinate of x, and the y coordinate is also x, right? Because it's on the line y equals x. Okay, now let me write something down. For each x, the cylindrical shell, you rotate that little line segment around a different line of rotation around that line. Okay. We have a cylindrical shell, a cylinder. We have the cylindrical shell determined by x. So later on, we are going to rotate the little line segment around a different line. You have a cylinder. That's in order to get the surface area of the cylinder, we need the base area. We need the base radius. We need the height. Okay. Has the. Now let's talk about the base radius first. Okay. I think Chad told me already. The base radius is denoted by r of x. Okay. Now follow the mouse cursor. The little line segment is here. So this time I should have drawn it a little bigger, but I hope you can follow me. The little line segment is here. You rotate the little line segment around a different vertical line. This time the vertical line has the equation x equals -1. Okay. Now we are going to imagine the base radius. The base radius is that length, right? That is the base radius. So do you see it's x plus 1, as Chad said? I hope the picture is not too messy, but now we are going to identify the height. I'm going to use h of x to denote the height. So anybody want to tell me the height, please? Anybody want to tell me the height? Look at that little line segment. You have this point has coordinates xx. This point has coordinates x squared. In particular, y coordinate is x squared. Y coordinate for this point is x. Anybody want to tell me the height x minus x squared? Yeah, the same as before. Actually, the same as before. Actually, it's kind of a pattern. The height is kind of the same. When you rotate around a different vertical line, you just figure out the base radius. So that makes sense. It's x minus x squared. So that is the height. So we got the height. Okay. I'm too eager to jump to step 3. After getting the base radius, after getting the height, we are ready to have the surface area. Okay. So the surface area of the cylindrical shell finally we integrate the area of cylindrical shells, and then we have the volume. Okay. Again, I do not want to introduce a notation for the cylinder. Now the volume is the integral from 1/3 to 1, the interval we got in step 1. And then you integrate the surface area of the cylindrical shell, you have the volume.